I'm Peter, and I'm going to approach a much smaller subject. I'm going to talk about guard nodes, which are a way to exchange storage space for simplicity and speed in code. They are a particular favorite of mine, which is why I picked this. A little background. I think we'll recognize the simple doubly linked list, which we built in the first week in data structures, where, and here I'm used to stepping out of the frame to point to things, but you said not to, where each node has a pointer to the next node in the chain and the previous node in the chain. The first node's previous pointer is just sitting out pointing to nothing, it's pointing to null, and the tail node's next pointer is pointing to null. What we keep for storage for the actual linked list is simply the head and the tail. If I were to build a doubly linked list that was guarded, I would still have the same three data nodes, but now my head pointer is pointing to a node marked dummy, which has no value that anyone's interested in, and my tail pointer is pointing to a node marked dummy, which has no value that anyone's interested in. Otherwise, the pointer is very much the same. Note that the head pointer's previous points to itself, and the tail pointer's next points to itself. Nothing is pointing to null. Okay, what is the possible advantage of this? And if I can get my code to come out, is that large enough to read? Okay, small problem. The keys I know to make it bigger aren't making it bigger. Anyone know how to do this off the top of their head and keep me from looking like an idiot? Command plus. No, and no. That's what I was trying. Okay, well, just imagine it. This is the code. This is the some of the code for linked list that was in the 1606 library solutions for data structures. And over here, I have it side by side with code for a guarded linked list. Yeah, that is a little hard to see, isn't it? Oh well. The nodes are the same. Next we come to the constructor functions. The constructor function for the linked list at line 9 is 1 line long. At line 11 is the constructor function for a guarded linked list, which is 5 lines long. Wait a minute, I thought I said it made the code shorter. In this case, it does make it longer, but the constructor is, of course, only called once for an entire linked list. Let's look instead at the add to tail function, which is a typical way of adding all of the nodes to a linked list. If you're going to have a linked list with 1,000 nodes, that's going to be called 1,000 times. In the original code, which comes first at line 17, there is an if statement. And the purpose of that statement is to determine whether or not the list is empty. If this dot tail, if there is a tail, then this tail, put the node after that, this dot tail dot next equals new node. Else take this new node we just created and put it at the head. So it doesn't know whether the list is empty or not, and it has to do a test in order to add the node to see whether there is a whether there are actually other nodes there to put it in between. On the other hand, the add to tail for linked list guarded at line 24 consists of 2 lines. One is to create the new node with its pointers pointing to the node before tail, which is the last useful node, and tail, which is the end node, and then one to have the previously last useful node point to it. This is not trivial to visualize, but what is happening is even if the list was empty, you're always going to be in the case where you're inserting a node between 2 other nodes, because even in an empty list, there will be a dummy tail node and a dummy head node. So there's no need to check to whether the node that I'm inserting has to become the tail node or the head node, because it never will. The dummies will sit there and prevent that from happening. As a result, the logic for add to tail is only 2 lines long and does not contain the if statement. And that, remember, that if statement was checked every single time you added a node. Let's say I'm putting 1,000 nodes in there. I just saved 1,000 if statements. So I find this code easier to read, and my personal opinion, and this does seem to be a matter of personal opinion, is that it's worth having the data structure be more complex. A very good teacher of mine once said that software design is the art of pushing evil from one place to another, because you can never get it quite out. So I prefer to have the evil, the part that doesn't quite make sense, be sitting in my dummy head and tail node in my data structure, which I'm not dealing with when I'm coding, and have my code for add to tail be 2 lines long. I also have the code here for removed tail both ways. It is 1 line short, starting at line 29 and 38. It's 1 line shorter. I do not want to step through each step in it, but I will just point out that again, there's a test at line 33 in the original way that says, if we have a tail, that test isn't necessary in the guarded list because it always has a tail and a head. So the guarded list has made the logic for manipulating the list shorter, simpler, and in parts that are repeated frequently, having 1 fewer if test, even though it does make the data structure a little odd and it indeed wastes space if space is a serious consideration. Whoops. Okay, the next slide concerns searching, and our developer is going to want to go to Africa and see if he or she can find any elephants in Africa. The developer starts at the southern tip of Africa, which I believe is the Cape of Good Hope, and it goes from the east coast to the west coast, and then north a little bit from the west coast to the east coast, and then north a little bit from the east coast to the west coast, basically turning Africa into a linked list. And at every node stopping and examining all the animals there and saying, is this animal an elephant? If it is, you exit, you've found an elephant. If it isn't, unfortunately, with that algorithm, you fall into the Mediterranean Sea. Okay, I thought I was going to get a laugh there. Thank you. In the traditional way that we did linked lists in junior phase, what that developer does instead is, as he traverses the linked list of Africa, every single point he says, is this animal an elephant? No. Am I at Tunis yet, which is the northernmost city that I can pronounce? No. Okay, go to the next spot. Is the animal an elephant? No. Am I at Tunis yet? And if he finds he's at Tunis, he stops, doesn't fall into the sea, returns nothing. But now he's had to do 2 checks at every single node. He's had to do twice the work. So the developer who likes guard nodes, whoops, that's falling in the ocean. The developer who likes guard nodes and doesn't know if there are elephants in Africa goes to Tunis and leaves an elephant there. Then goes down to the Cape of Good Hope, traverses Africa the way we're speaking about, but at every test, all he has to test is the animal that I'm looking at an elephant? If there are elephants in Africa, he or she will find one somewhere around here and exit. If there are no elephants in Africa, he or she will end up finding this elephant in Tunis that he put there and say, yes, I found an elephant. Is it the elephant I put in Tunis? That's only 1 check for position. Yes, it's the elephant I put in Tunis. There are no elephants in Africa. This is implemented, just to go back to actual linked lists. We're looking for 27. Every time we say, no, I don't have a 27, I have to say, is there a next node? Yes, there's a next node, look, 23. Let's skip some of this. 102, yes, there's a next node, 17, not 20. The 27 that I'm looking for, was there a next node? No, so it wasn't found. If you put in a linked list with guard nodes, you actually take the value you're searching for, the 27, and you write it to the tail node before you start searching. So you say, okay, did I find a 23? A 27, sorry, I'm looking for 27. No, 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 no. All I'm checking is 27. I'm not checking, are there any more nodes? I found a 27. Is it my tail node? Yes, I didn't find anything. So I've got half the number of tests. Another thing that we do fairly frequently is merging 2 lists. And the traditional way to merge the 2 lists is to look at the 2 pointers, take the lowest value, stick it at the bottom, and move the pointer. We've got 7 and 8. You take the 7, which is the lowest value, and move that pointer over to 10. Typically, you get to an end case where you take this 12, you've moved off the end of one list, and you have to completely drain the other list, which is special case code. If, on the other hand, you have guard nodes, you write infinity into the last node in each one. And then your test is, if my pointer in the first array points to a smaller number, take it and move the arrow. Otherwise, I test and see, am I at infinity and infinity? If I'm not, I take the one from the bottom and move its pointer, and otherwise I go on. So I'm only doing the at the end test 50% of the time. So I'm doing fewer tests, and I never run off the end and have to have special cased code to completely drain the smaller list. So thank you for listening. I hope that you find guard nodes as interesting as I do.